Hello. So we missed a class last week. I believe it was the Tuesday class. Just completely slipped my mind. So we're gonna replace that with today. Okay, so today we're gonna continue with temperature. All right. And then after that, if we have a bit of time, we'll start the next chapter. Okay, let's get started. So let's look at question 1. You have a resistance thermometer, which this is a thermistor, and a thermocouple thermometer used at the same time to measure the temperature of a water bath. Explain why, although both measurements have been calibrated correctly and are at equilibrium, they may record different temperatures. So why do you think that is? So just because they have been calibrated correctly, it doesn't mean that the temperatures are accurate, because the resistance and the temperature, they are not linearly proportional, right? Remember, this is the resistance, this is the temperature. It kind of looks like a 1/x graph. And then for a thermocouple, the voltage and the temperature, they might be, some other curve or line that may or may not correspond to this one over here at a specific temperature. So for a given temperature, both of these may record different readings. I mean, obviously they would record different readings because one is in resistance, one is in voltage, but the way you calibrate it is you pick 2 points and then you divide by however many intervals that you want. Kind of like when you are calibrating a mercury in glass thermometer. So you're doing the same for the thermocouple, right? So because the variation of the sensing parameter to the temperature is different, they're not linear, therefore you can't assume that they would have the same temperatures, if that makes sense. So you say, since sensing parameter, resistance or potential difference is not linear to temperature, they may record different temperatures. Then for part B, state what is meant by the absolute scale of temperature. So the absolute scale of temperature is a scale that is independent of the physical property of an object. So it only depends on, say, things like kinetic energy, which is not a physical property. Physical property is something that you can measure. So kinetic energy is not something that you can measure, right? So it is a scale that is independent of the physical properties of a body. So that's what it means. Part C, state what is meant by the absolute zero of temperature. So we did this in the last chapter. The absolute zero just means the mean kinetic energy is 0 or a minimum. So mean kinetic energy is a minimum. Okay, so here you just say mean kinetic energy. You don't have to say mean translational kinetic energy, because we're not referring to ideal gases specifically. Okay, let's look at question 2. The resistance of a thermistor at 0 degrees is this guy, At 100 degrees, you get this guy. When the thermistor is placed in water at a particular constant temperature, its resistance is 2003. Assume that the resistance of the thermistors varies linearly with temperature. Calculate the temperature of the water. Okay. So as you can see, as the temperature rises, the resistance decreases, and we're going to assume that it varies linearly. So it kind of looks like a R. This is temperature, and it goes down like that. Okay. So something like this. RTK, and T must be in kelvins, by the way. So initially you have 3840, and then your T is 273. So that's your K. All right. Wait a minute, will they give you the same thing? This should be the same as 190 times 100 plus 273. I feel like this might not give you the same thing though. Hang on, let me just check. 373 times 190 is 70,000. Yeah, you don't get the same. So the proportionality constant is not the same. Hang on, how do I go about doing this again? Let me think. So you should get about 42 degrees. Oh, wait, sorry, what am I doing? No. So just now I wrote R equals to K over T, but this actually means the graph would look like this. So it's not linear actually. So we're assuming it's linear, which means it has to be R is equals to some number times T plus C, right? Because it looks like a straight line. So initially R is 3840. K is going to be some unknown. T is 273. C is another unknown. It's equation 1. We're going to do the same thing over here. We have 190 equals to K times 373 plus C. Equation 2. So we're going to take equation 1 minus equation 2. We get 3650 negative 100K. C's cancel, so we get negative 3.65. There we go. And then we can find C. Okay. So the water has a resistance of this guy, right? When you put the thermistor, you get a resistance of 2003. So 2003 equals to K times the temperature plus C. So temperature must be 2300 minus C over K. And what did we get? We're going to end up with 694.9792, sorry, degrees Celsius. No, sorry, this is in kelvins. This is in kelvins. And now we change it back to degrees Celsius. So we have to subtract 273, which gives us... Wait a minute. That is way too large. What? Oh, sorry. I messed up my K. My K should be 36.5. Hmm? Okay, C should be 13804.5. $315 degrees Celsius. Sorry, kelvins. Then subtract that with 273. We get 42.2 degrees Celsius. And that's the temperature of the water. There you go. Okay. Moving on. The temperature of the water as measured on the thermodynamic scale of temperature is 286. What is meant by the thermodynamic scale of temperature? And comment on your answer in A. Alright, so again, this is what we've just done. The thermodynamic scale just means the scale that is independent of the physical property of the object. So this temperature that we get here is dependent on the resistance of the thermistor. So it depends on the physical property of an object, aka the thermistor. But according to the thermodynamic scale, so the true temperature that we measure is actually 286. So this is independent of the physical property of a body. So what is 286 kelvins? 286 kelvins minus 273 is 13 degrees Celsius. So this guy is in fact 13 degrees Celsius. So according to the true scale, it is 13 degrees Celsius. But according to what we've measured on the thermistor, we got 42.2. So why is there a discrepancy between these two? So the reason there's a discrepancy is again because the thermistor is not actually linear. So this assumption is not really accurate because it's technically 1 over x. Okay, so because the calibration curve is non-linear, therefore that's why you end up with this discrepancy. In fact, for this chapter, whenever you see them asking you like, why is there a difference between the thermodynamic scale with the measured temperature, the answer is almost always because the scale is not linear. Okay, so there is a discrepancy between the thermodynamic scale and the measured reading, because the resistance does not vary linearly with temperature. There you go. Okay, you guys good? Moving on. So now we are given an EMF generated by the thermocouple. Remember, the thermocouple is a thermometer with the potential difference as the sensing parameter. And then you are given this curve here. By reference to the figure above, state 2 disadvantages of using the thermocouple when the EMF is about 1 millivolts. So if I measure something with the thermocouple, and on the thermocouple it shows me 1 millivolts, and then I cross-reference that with the calibration curve of the thermocouple, we get two possible points. It could be this point here. It could also be this point there, right? So that means the temperature could be either something like 375 or maybe 680. We don't know. And that is one of the disadvantages. Right, so one of them is we have two possible T values. What is the other disadvantage? What do you guys think? So the other disadvantage has to do with the fact that below 1, you can see this is almost like a straight line. So it's almost linear, but after 1, you can see that it curves quite significantly. And around 1, yeah, so after this point here, it starts to curve quite a bit. So the variation is non-linear. There. Okay, and that's it. We are done. This chapter is, like I said, very short. There's nothing much to it. Okay. Moving on to chapter 19. So technically I've grouped 18 and 19 together in the past years, because 18 is a very short chapter, so. Okay, we are done. So you should have these with you. If you don't have this yet, you can download them from Google Classroom. So the slides and the notes are all there. Chapter 19. So for chapter 19, we're going to be looking at the heat capacities and latent heat of a substance. If you have done a bit of chemistry, these would seem very familiar. And then later on, we look at the first law of thermodynamics. And we're going to try to solve a couple of problems involving the first law. And also there's the idea of the internal energy of a matter. Usually they will talk about internal energy of an ideal gas. So we'll talk about that soon. So there are 4 different states of matter: solid, liquid, gas, plasma. And the further you go along this line here, the more energy you have. So solids don't really move about much. They sort of vibrate in place. Liquids sort of slosh around. Gases have very large kinetic energy for each particle, but very low potential energy. So what exactly does potential energy mean when you're talking about the microscopic state of matter? So the potential energy, you can think of it as the force of attraction between the particles. So for solids, the potential energy is very large, and then as you go along here, the potential energy decreases. Okay, and plasma is it's a bit like, so you get plasma on the surface of the sun only at extreme temperatures. So plasma is not really in the syllabus, so you can just ignore this one for now. So we're just going to be looking at these three. Okay, so we're going to start off with the definition of internal energy. So the internal energy is the sum of the random distribution of potential and kinetic energies of the particles. So you write it as U, and that's the sum of all the kinetic energy of all the particles, plus the sum of all the potential energy of all the particles, and that's how you get the internal energy of the particles. Okay. You can write it down on the notes right here. Okay, moving on. Next up, we have the specific heat capacity. So what exactly is the specific heat capacity? It is how much energy you need per unit mass to change the temperature of the substance by 1 kelvins. So the higher the specific heat capacity of an object, the harder it is to increase the temperature of an object. So for example, water has a heat capacity, specific heat capacity of, I think, 4.2 joules per kilograms. I think so, yeah, something like that. So if you want to increase 1 kilogram of water by 1 kelvins, you need to introduce 4.2 joules of energy. Okay. If you put impurities into the water, you might change the specific heat capacity of the substance. So maybe if you put in some salt or you put in some other substance, you mix it around. So now the specific heat capacity rises to 10 joules per kilogram per Kelvin. So you need to heat the water longer for it to start boiling. Assuming, of course, that the boiling temperature is still 100 degrees Celsius. Usually when you add impurities to the water, the boiling temperature might change as well. But yeah, essentially it tells you how difficult it is to increase the temperature of a substance. And the equation associated with this is Q is equals to mc T. So T here, technically you should put a delta. Yeah, so technically there are two deltas here. So delta T here is the change in temperature of the substance. And then this guy here is the change, or I wouldn't say a change, it's more like the energy or heat introduced to the system. This M here is the mass of the system, and C is your specific heat capacity. So if you rearrange and make C the subject, you will get C is equals to delta Q over M delta T. So it is the energy required per unit mass per unit increase of 1 kelvins. Okay. Right. Yeah. So, the equipartition theorem. All right. So this one is not technically in your syllabus, but I'll just very briefly mention this because I think it's interesting to know. So the equipartition theorem tells us that if you introduce energy to a system, the energy is going to be distributed evenly to all the modes of the system, or sometimes people refer to it as the degrees of freedom of a system. So what exactly is a mode or degree of freedom of a system? Well, it depends on the configuration of the molecules. But generally, there are three kinds of degrees of freedom. You have translational, which means it moves left and right, up and down, backwards and forwards. So that's translational. That's the first degree of freedom. And then the second degree of freedom is rotational. It could rotate in the z-axis, the x-axis, or the y-axis. And the third degree of freedom is vibrational. So it kind of oscillates along the z, x, or y-axis. So typically for solids or complex molecules, you have all three modes, okay? Rotational, vibrational, and translational. However, when we measure the temperature of a substance, only the translational kinetic energy plays a part in the temperature. So whatever we get on the thermometer depends only on the translational kinetic energy. So imagine this, if I take a solid substance, okay, and it has 3 modes of freedom, 3 degrees of freedom, and I put in 9 joules of energy into the solid object. So this 9 joules of energy, according to the equipartition theorem, is going to split equally into 3 modes of movement. It's going to get 3 joules in translational, 3 joules in rotational, 3 joules in vibrational. And then when we measure our thermometer, the thermometer would only pick up on this 3 joules here. So it only increases the temperature by a tiny amount. Now, if you compare this to, say, an ideal gas, right? So now you have an ideal gas, and you put in 9 joules of energy into the ideal gas. So remember, an ideal gas only has a translational degree of freedom. It doesn't have rotational or vibrational. So all the energy that you put into the ideal gas goes to translational. So the temperature rises very quickly because the temperature only depends on the translational kinetic energy. So depending on the different kind of substances you have, you might have 1 mode or 2 modes, or these 2 modes, or maybe all 3 modes together. So the more degrees of freedom you have, the harder it is to increase the temperature of a substance. Okay, so that's why different things have different specific heat capacities. There's actually more to it than that, but this is just a very brief overview of the equipartition theorem so that it kind of makes sense, hopefully, in your head. Okay, moving on, let's look at how exactly do we measure the specific heat capacity of a substance. All right, so this is the kind of setup that you want to do if you want to measure the C of the substance. So let's say you want to measure the specific heat capacity of this metal cylinder. Okay, so this metal substance, maybe it's aluminium, whatever, right? So this metallic solid, you want to measure the specific heat capacity. So what you would do is you would cover it with some insulation, so maybe some cloth or something like that. You need to know how to set this up because we're going to be using this for paper 5, which is a planning experiment. A planning paper. Okay, so it helps to know how to set it up. And there are certain questions in paper 4 where they ask you how to set up this experiment. So you need to know every single step. So the first thing you do is you wrap it up in some insulation to prevent heat loss, okay? And then you set up the circuit as shown like this. You want to draw it out if you can. So what's going to happen here is you're going to supply some current through the heater, and this heater is going to heat up the metal cylinder, and you want to heat it up slowly. Okay, and the reason you do that is to make sure that heat is distributed uniformly throughout the metal cylinder. And then you want to allow some time for the thermometer to reach thermal equilibrium before you take a measurement. So initially you take an initial measurement, and then after some time you take another measurement. So that would be the change in your temperature. So remember that C is equals to energy over M times change in temperature, right? And the original equation was this guy is equals to mc delta T, like so. So M you can measure before the experiment by putting this metal cylinder on a weighing balance. Okay, so we've got M. And the two variables here in this experiment is actually delta Q and delta T. This C is actually a constant. So if you were to plot a graph of delta Q against delta T, you would actually expect to see a straight line that passes through the origin. And the gradient of this straight line is going to be equals to C. So how do I get a line? Well, you're going to need multiple values of delta Q and delta T. So how do you get multiple values? You repeat the experiment multiple times, and then you're going to get like a bunch of points, and then you draw the line of best fit. And then from the line of best fit, you can work out the gradient using what you have done in paper 3 from AS, okay? But how do I find the energy supplied to the metal cylinder? Well, we have some voltage, we have the ammeter here, and you know that the power is actually equals to work done per unit time. So work done is actually equivalent to the energy, okay? So PT is equals to delta Q. And you know from AS that power is equals to IV. So there you go. Delta Q is actually the current times the potential difference times how much time you have taken how much time you have waited before you've taken the reading on the thermometer. So maybe you wait for a minute, then T would be 60 seconds. So when you're doing this experiment, you have to make sure that your I and your V are constant. Okay? So it's usually quite useful to have, what do you call that? What's the name of that thing again? A rheostat, yeah. So you want to have like a rheostat over here. This one is actually called a rheostat. A rheostat is like a variable resistor. Okay, the reason you want a variable resistor is because as your experiment goes on, the wires are going to heat up, which means the resistance of your system is going to go up, which means your current is going to drop, okay, which is going to affect this I here. So as you're carrying out the experiment, you should subtly adjust the rheostat to make sure that the current stays constant. Okay, because you want the power to be constant so that you can get P times T. Rheostats are like potentiometers, but very precise. It's similar to a potentiometer, but they are not the same because a potentiometer is used to find the EMF of the test cell. But a potentiometer, but a rheostat's purpose is to vary the resistance. So they are similar, but not quite the same. Yeah. How do they work on the same principle? If you draw the circuit out, it kind of looks similar because the potentiometer kind of looks like this, and then you have like a variable resistor like so, and then there's like a junction here, and then this is your test cell, and then like this. So usually this guy here, this thing is a rheostat or variable resistor. But the whole thing, this whole thing is called a potentiometer. So I suppose you could say a potentiometer may contain a rheostat, but a rheostat is not a potentiometer, if that makes sense. Yeah. All right, so you want to take multiple readings of this guy and this guy, delta Q and delta T, and then you get multiple points, plot your line of best fit that goes through the origin, find your gradient, and that is your C. Well, sorry, your gradient is actually M times C. This whole thing is your gradient. So your C is actually your gradient divided by the mass of your object. There. Okay. Hopefully this is good. I think there's it's actually here. By the way, in the notes, whenever you see like a solid bar over here on the left, that means it's actually not part of your syllabus. You can skip this part if you don't want to. This is just for extra reading. So, yep, it's all here. Part C, page 3. Okay, it's all here. And yep, all there. So if you want to review this part, you can just refer to your notes. Okay, next up we have the specific latent heat. So the specific latent heat is the energy required to change the state of a substance per unit mass without any change in temperature. So whenever you heat something, let's say water, right? You put I'm not sure whether you've noticed this in chemistry or biology, but if you put a thermometer in a beaker and you heat it up, the temperature is going to rise all the way to 100, and then it's going to stay constant at 100. So it's going to stay at 100, and then you get this water boiling off, but it's not going to go higher than 100. Okay, so that's where this comes into play. So suppose I want to evaporate or boil away 1 kilogram of water. How much energy do I need? So the answer has to do with the specific latent heat. So let's say the specific latent heat is 10 joules per kilogram. That means if I want to boil away 1 kilogram of water, I need 10 joules of energy. But this is assuming that the water is already boiling in the first place. Okay, the 10 joules does not include the energy that you need to get the water to boil. So if the water is at room temperature, you need to put in energy to get it to boiling temperature. and then you need 10 joules per kilogram to boil away the water. Oh, sorry, 10 joules to boil per 1 kilogram of water away. Okay? So the specific latent heat is written as delta Q equals to delta M times L. So here it's slightly different because if you remember, the one that we had earlier was delta Q equals to MC delta T. So the variables are Q and T for the last one, but for this one, the variables are Q and M because the M, which is the water that is being boiled away, is actually the variable here. So the substance involved in a change of state. So this doesn't necessarily mean liquid to gas. It can also mean solids to liquid. So some ice melting, or maybe solid to gas. Okay. What's the term for the phase change from solid to gas again? I remember there's a specific name for it, but I can't remember what it is. For those of you doing chemistry, what was it again? Usually you use that for, say, carbon dioxide. So if you have dry ice, which is basically solid carbon dioxide, and you put it in room temperature, it's going to immediately vaporize into air. So it just goes from solid to gas instead of going through liquid. Sublimation, yes, that's correct. That's right. Thank you. Okay. So there are two kinds of specific latent heat. There's a specific latent heat of fusion and specific latent heat of vaporization. So specific latent heat of fusion is the energy required to convert unit mass of solid to liquid. So you're going from solid to liquid with no change in temperature. You can write that down on your notes. Where is it again? There we go. All right, energy required to convert unit mass of solid to liquid. Fusion. So use the kinetic theory of matter to explain why melting requires energy, but there is no change in temperature. So if you introduce energy to a substance, shouldn't it, increase the mean translational kinetic energy? Then wouldn't that increase your temperature? Usually yes, but when it is on the verge of a phase change, the energy is actually being used to overcome the bonds holding the molecules together. Right, so you want to say something like this. The bonds between the particles are weakened as the molecules move further apart. Kinetic energy is unchanged, so temperature is unchanged. Potential energy is increased, so energy is required. So when you move the particles further apart, the potential energy would increase. So the potential energy tells you the strength of the bond, but it also, you can think of it as the further that the particles are, the greater the potential energy, in a way. You can think of it like that. Okay, so if you want to change the state of a particle, you have to, if you want to change the state of a body, you have to increase the separation between the particles, right? For example, you're going from solid to liquid, the particles are further apart. So if you want to move them further apart, you have to increase the potential energy. So this is kind of like the standard answer that you want to quote whenever they ask you something like that. Okay. Can we move to the next part? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, moving on. We have the specific latent heat of vaporization. So the only difference between this one and this one is that it is the energy required to convert unit mass of liquid to gas with no change in temperature. This is a keyword, by the way. You want to write this phrase down in the exam. Otherwise, you're going to lose a mark. Explain why the specific latent heat of vaporization is higher than the specific latent heat of fusion for the same substance. So, in fact, yeah, if you go from solid to liquid, let's say you're melting ice, you actually need less energy than if you were to go from liquid to gas. Why do you think that is? So going from solid to a liquid requires more energy than going from liquid to gas. Why? Because it's already losing energy. But they're both losing energy though. I mean, the substance that gets converted to the next state carries the energy away with them. So they're both losing energy. But why do you need more energy to go from liquid to gas? Okay. Here's a little hint. If I take 1 kilogram of ice and I compare that with 1 kilogram of water, the bond is stronger because you need to overcome gravity to separate the molecules. The bond is stronger. Let me think. I'm not sure whether the bond is stronger plays a part here. It might very well be true, but I'm not sure if that is the reason for it. Yeah, I don't think that's the reason for it. Because you need to overcome gravity to separate the molecules. The gravity, so the masses of the molecules are actually very small. So gravitational force between them is, you could pretty much ignore them. In fact, the bonds you get between molecules, like the ionic bonds, covalent bonds, polar molecules, and things like that, they're all electromagnetic forces. Electric forces, you can think of it as the electric forces, like between a positive and negative charge. So, and the electromagnetic force is so much stronger than the gravitational force. So you can pretty much ignore gravitational forces when it comes to the bond between molecules. So think of it like this. If you have 1 kilogram of ice and 1 kilogram of water, what's the difference in the volume? Not that much, right? I mean, the water would obviously have a larger volume because the average separation between the particles are greater. But if you compare 1 kilogram of liquid water to 1 kilogram of water vapor, the 1 kilogram of water vapor is going to occupy a much larger space, right? For those of you who have done chemistry would probably realize this. It occupies a much larger space. So going from solid to liquid, the change in volume is very little. But going from liquid to gas, the change in volume is enormous because the change in the separation is so big. And also, because of that, if you're going from liquid to gas, when you change to a gas particle, you have to push back the atmosphere. So you're doing work against the atmosphere, which is why you need more energy being supplied to the liquid water to push back the atmosphere. So that's one of the main reasons. All right, so as the substance transitions from liquid to gas, it expands, doing work against the atmosphere, hence it requires more energy. So that's the reason. Does that make sense? Okay, let's continue. So, explain why evaporation occurs even at temperatures below boiling point. So, we know that these particles, these liquid particles, become gas particles because you have supplied enough energy and then it breaks free from the surface of the liquid and becomes a gas particle, right? So why is it that evaporation occurs even at temperatures below the boiling point? Why do you think that is? Even at, say, room temperature, you still get water evaporating, right? You don't have to boil the water for it to evaporate. So why is it evaporating even though we are not supplying energy to the water molecules? Why do you think that is? Energy slowly trickles into the water. Okay, if energy slowly trickles into the water, you would expect the temperature to go up, right? Suppose you put like a thermometer in the water. Would you expect the temperature to go up gradually over time? I don't think so, because it should have thermal equilibrium with the room. So if your room temperature is 25 degrees Celsius, your bucket of water is going to be 25 degrees Celsius as well. Atom decay? Oh, you mean like nuclear decay? Uh, uh, well, even okay. There's the problem with that is nuclear decay isn't quite as fast as if the rate of evaporation, because if water decays as fast as it evaporates, then maybe there might be some kind of correlation between water decaying and it evaporating, right? But water doesn't actually, like, the half-life of water is you know what, I'm actually curious now. What is the half-life of water? Half-life of water. The biological half-life of water in a human being is about 9 to 10 days. 9 to 10 days. Does water have a half-life? It's about 7 to 14 days. Okay, so it decays in about a week to a fortnight. So you're gonna have to wait for about a week for the bucket of water to go down by half. I mean, assuming that is the reason behind it, but it isn't, so no. um, Still a good guess though, even though it's a little unusual, but it's a good guess. So the reason it evaporates at temperatures below boiling point has to do with the meaning of temperature. So you know that temperature is proportional to the mean translational kinetic energy. And the keyword here is mean. So if your temperature is 25 degrees Celsius, that means the mean translational kinetic energy is some amount. But does that mean all the particles have that kinetic energy? No. There are some particles which are much faster, there's some which are much slower. So those particles which are much faster, which happen to be at the surface of the water, would evaporate, would escape into the air. Okay, so you want to say this. Temperature depends on the average translational kinetic energy, so not all particles possess the same amount of kinetic energy. Sufficiently energetic particles on the surface of a substance will escape the liquid in the form of a gas. Okay, so what happens when the most energetic particle escape from a liquid? For example, let's say we are, okay, how should I explain this? So imagine a normal distribution, okay? Let's say this is the kinetic energy of the gas particles, and this is the number of gas particles. So it kind of looks like a normal distribution, kind of like this. So the mean is actually over here. Okay, so what happens to the mean if you remove some of the highly energetic particles? So maybe if your kinetic energy, sorry, I messed up. This one should be KE, this one should be N. N should be here, and this should be EK, right there. Okay, so maybe if you exceed this point, then it's going to start to evaporate. So that means after a while, all these particles here are going to evaporate into thin air. So what's going to happen to your mean kinetic energy then? It's going to go down, right? Because all the energetic particles are gone. So now your new mean is going to drop down to this over here. So if your new mean is decreasing, that means your temperature must also decrease, because the temperature depends on the mean kinetic energy. So this is the working principle behind why we sweat. So after some intense workout, you get all sweaty, right? And then the sweat evaporates. So what happens when the sweat evaporates? The energetic particles evaporates, which means the mean kinetic energy of your water molecules in your body decreases, which means your body temperature decreases, which is kind of the point of sweating, because your body is heating up when you run and do all this exercise. So you want to sweat to reduce your body temperature. So there you go. Okay. Explain why a cooling effect accompanies evaporation. Okay, I've accidentally given you the answer here. So, as some of the most energetic particles leave the surface of the substance via evaporation, the average translational kinetic energy of the substance drops, reducing the temperature, hence the cooling effect. There you go. Okay, so essentially that's it. I think we're gonna stop here for today. I think we're pretty much done with the theory part of this chapter. There's a little extra here. We'll do this tomorrow. And then we'll do the first law of thermodynamics, and then we'll do some questions tomorrow. Hopefully we can get through most of this. I don't think we can go through every single question, because this is actually quite a lengthy chapter, but we'll see what we can. We'll see what we can do. Wait, let me think. Tomorrow we have a class, and then Friday we have a class, and Wednesday we have another class. I think Friday we can't actually have our class. We might have to cancel the class on Friday because we have the e-graduation for your seniors on Friday. So most likely this week we will only be doing tomorrow and Wednesday. Yep. Okay, so we shall stop here for today. Bye bye. I'll see you guys tomorrow.